So we'll have three more presentation to go. So the first one for this session will be given by Malcolm Roberts from UK, and the title is Global Modeling of Climate Process at High Resolution, from one model towards multi-models. Yes, welcome, Roberts.
And thank you to the organizers for inviting me. I've had a very nice weekend, my first time in Taipei, so thank you very much. And I hope in real life I look slightly better than my photograph. I'm sorry that my photograph looks quite that bad. What I want to talk about is kind of modeling at high resolution and really towards looking at multi-model. So we've heard already today, and I'm sure we'll hear today and tomorrow a lot about the results of high resolution and how high resolution improves our representation of important climate processes. What we've been working on for the last 10 years, actually, we just passed our 10-year anniversary, myself and Pierluigi Fadale, collaborating in Japan initially at the Earth Simulator, building up a hierarchy of model resolutions to really investigate at what resolution do you represent processes adequately. Are there, do they converge at a particular resolution? Do we have to keep going up and up and up, or are there some things that we can say, yes, at 60 kilometer resolution we do a good enough job of this thing, or at 25 kilometers we do a good enough job? So that's kind of where we're looking at, is what processes emerge, what gets better as we increase the resolution. Okay. So I'm just going to have a couple of examples from a recent project, Upscale, that we were involved in, that we ran, and a couple of science highlights from that project, and then kind of using that to motivate this idea of a multimodal comparison as part of CMIP6, which I had some discussion in Japan last week, and I believe we're going to have a discussion session tomorrow on kind of international collaboration aspects. So I'll introduce our ideas, and I'm sure there'll be questions today and tomorrow about whether it's too much, whether it's too demanding, whether we need to do the particular protocol that we're suggesting, and very much want to kind of get input into that to get as many groups as possible involved in that proposal. I'll then say a little bit about some more regional work that my colleague Elizabeth Kendon has been involved in, down to a 1.5 kilometer resolution over the UK, and looking at extreme rainfall in that regard. But I'll first talk about kind of global modeling. So as I say, we've been working on this really for the last 10 years. So 10 years ago in Japan, we essentially started with this resolution, which for the Met Office has been our resolution at CMIP3 and CMIP5. So it seems like a long time to essentially sit at 130 kilometers as our baseline resolution, given that we know, over the last few years certainly, that is not a good enough resolution to do many important climate processes. But because we increase the complexity, we add Earth system components, we make it much more expensive, and because obviously with CMIP there are many simulations we have to do. We have to do hundreds, thousands of years of simulation, ensemble members, and all kinds of things. It makes it very expensive. But that's quite low resolution, and that's a typical resolution, I think, of a lot of CMIP5 models. And so that's kind of idea, is we really want to look at, if you increase the physical resolution, so if you essentially stick to the physical model and leave a lot of the Earth system complexity out of the model, and then increase the model in a hierarchy, so actually looking at different atmosphere resolutions and to some extent ocean resolutions as well, where we really try very hard to leave the physics and dynamics as similar as possible as we change the resolution. So we have to change the time step and some other things to actually make it work. We really tried quite hard through probably this range, maybe up to 12 kilometers, and then maybe playing with explicit convection. You might want to do something different. but probably in this range, really try and keep the hierarchy as pure as possible, to understand what comes from the resolution itself. You know, you can tune your physics part way up, but that means you're not looking at resolution anymore, you're looking at changes in physics. Now you can argue that at some point maybe your physics isn't good enough or isn't really ideally suited for that resolution, and that's fine, but that means you're not looking at resolution anymore, you're looking at other things as well. So that's what we've been trying to do. So you can see here, so I'll say that's where our climate resolution has been for 5-10 years. This is where we hope to get to somewhere around here for CMIP6, so using the quarter-degree ocean, which again will make it much more expensive, but using an atmosphere resolution, hopefully one of these two, depending on how affordable they are. So you can see here, so I should probably say that essentially the climate model that we use is the same as the weather forecasting model, so it's very much the same system and it's proven every day on the weather forecasting side too. And then the seasonal forecast is Glossy 5, that uses that resolution here as well, so that's proven over seasonal forecasts, kind of basically run every day, every week. So we have a lot of kind of assessment of the model. And then this upscale project, which I'll go on to present in a minute, we've done an ensemble of essentially 25-kilometer atmosphere comparing to 60-kilometer, comparing to 130-kilometer, with a few ensemble members each, with a view again of looking at what does resolution bring, what does it really change. And this is kind of what we really are looking for. Apologies if this is a bit small, but it's just kind of an indication of what we're trying to do here. So for a given process, we're looking, as you kind of move away in this little mind map, at different processes. What we'd like to get to at the end is what resolution is sufficient, or whether we say, actually, we haven't got to a resolution that's good enough to do that process really properly yet. So most of the references here are from kind of UK studies, because that's what we know best. Hopefully, over time, we can kind of improve this and have references from other groups and their evidence. But as you follow it out, you can see processes that we've tended to look at so far, and then some idea of what resolution we find either does a good enough job, or as I say, we haven't got to, then not enough of these heavier events that we see in, say, TRIM observations. Now, although the parameterized model doesn't do a great job, we do see, as we increase the resolution, that it does at least move this way. So you do get somewhat more of the intense rainfall, not the observations, but it does improve. And we do find that 25 kilometer does do a better job than 130 kilometer. So it's not perfect, and in this case, with a short run with explicit convection, it does a remarkably good job of the extreme rainfall, but we can't run that for long enough because it's too expensive. But I think that's indicative of some of the processes that we're interested in looking at and understanding why the resolution does actually give you a better simulation. So this is the upscale project that we ran a couple of years ago. We were given a grant to PRACE is kind of European supercomputing time that you can bid into, make proposals into. And we were lucky enough a couple of years ago to get about 140 million core hours on a machine in Germany for 1 year. So we had 1 year to get on the machine, port the model, do the simulations, get the data off, and get off the machine. So what we did is we did some ensemble members, so 5 ensemble members at 25 kilometer resolution, 3 at 60 and 5 at 130. For both present day, so there's present day simulations, and then also a future time slice simulation with a methodology similar to what we heard earlier. So taking delta SST, in this case from just our CMIP5 model, under an RCP 8.5. So it's just a simple delta. And again, to try and look at, over this period, look at the impact of model resolution, what changes, can we understand why those things change. And so there's a bunch of references here of papers that are already published or in press, or in preparation on this work. So the first one is large-scale energy and moisture transports, and talk a bit about that. So Marie-Estelle Demery, from essentially 10 years ago, she's been working on this kind of area from when we started in Japan. And so what we have here is, after Trembirth, a kind of figure of the different radiative fluxes that you find in the atmosphere for a couple of model generations. So Hadjim 1 was CMIP 3 essentially, and actually Hadjim 3 is post CMIP 5, so it's a model that we've been developing since CMIP 5. And so you can look through at the different model resolutions. There's a couple of reanalyses here, and then the black figures are from observations. So you can kind of look through all of these fluxes, and in general the model does a good job of the radiative fluxes. Probably the biggest bias is it has too much surface shortwave at the surface, and that actually then has too much latent heat, so it kind of tends to remove the energy that's excess at the surface by getting too much latent heat and too much precipitation over land. But on the whole, the model does a good job. And on the whole, the radiative fluxes don't change very much with resolution. So there's small changes to perhaps the TOA and other things, but in general, they stay much the same, as I say, with our clean hierarchy, so not changing the parameters very much with resolution. And they're pretty consistent with the Wild et al. And the Stevens et al. Schematics. However, when we look at the hydrological cycle, we do see some changes with resolution. In particular, we find as we increase the resolution, we reduce the amount of precipitation over the ocean in both generations of model, and actually increase the precipitation over land. Now, actually, over land, this makes the bias worse. So you can see we already have too much precipitation, and actually makes it worse. But as I say, that's partly at least due to this excess shortwave at the surface that's inducing that bias. And then, as you'd then expect, so there's an increase in the moisture transport from ocean to land, and so essentially this whole hydrological cycle gets stronger as we increase the resolution. So if you then plot aspects of that against the resolution, so here we have resolution increasing, here's a 130 kilometer model, out to 25 kilometers here, and you look at a couple of if you look at that in a couple of ways, so either the transport of water from ocean to land in the red, or a measure of the local recycling of precipitation, which is essentially looking at the balance between like a column evaporating, precipitating, so just kind of in place, which I think typically low resolution models do too much of. You know, they evaporate in one place and then essentially precipitate the same place. That against horizontal kind of zonal movement of moisture, say from ocean to land. So you can see as you increase the resolution, you see quite a big change in that. So essentially you're having less of this local recycling and more of the zonal transport, such that it seems to, in our model, converge. 60 kilometer is about where it converges, and then it doesn't change so much going up to 25 kilometers. So it would seem for this model that 60 kilometers is perhaps the resolution that you need to do a decent job of this. So there's a couple of observations here with some kind of range. So we think this is better than the low resolution, and it seems that 60 odd kilometers is good enough for this, for our model. I'll then quickly say something about the hurricanes and tropical cyclones within the model. There are many people in the audience much more expert than me on tropical cyclones, so I won't kind of dwell on this too much. But again, it's just illustrative of a smaller scale feature, so that the hydrological cycle is a large scale feature that changes the resolution. These are obviously much smaller scale features. But as you see with the track density, as you increase the resolution from 130 to 60 to 25, there are regions that get worse. So the Central Pacific kind of has this constant stream of tropical cyclones, and the eastern Pacific is too much. But you can see, particularly in the Atlantic, at low resolution, we essentially have very few more in the eastern Atlantic, and they're all kind of in the Gulf of Mexico. But as we increase the resolution, that seems to improve, get a bit more like the Hurd hurricane observations. The model has too many in the southern hemisphere, but I think in general this high resolution distribution is better. And we have been trying to understand what causes the improvement in the Atlantic, and I think we're kind of picking apart that in terms of some aspects of the large-scale circulation. So there seems to be some relation to soil moisture or features over Africa, which then influences the African easterly jet. So here's the African easterly jet as a kind of zonal mean with latitude. And you can see that as you increase the resolution from the low to the middle to the high, you both shift the axis of the jet a bit northwards to more like the observations, and also sharpen up the front on the south edge. I think the southern part is where the African easterly waves tend to form, that form tropical cyclones earlier in the Atlantic. So obviously, if with a weaker and further south jet, you're not going to produce as many African easterly waves as the improved state. And actually here, for reference, the Glossy 5 model, so that's N216, so it's essentially the same model as this one, but with a coupled and initialization and some other things, does an even better job and actually gets many more tropical cyclones in the East Atlantic. So again, something to understand there. What is it about that? Is it the initialization? Is it the coupling? Are there other things in there we can understand why that model is better? But then all of that together then gives you a much better intraannual variability in the high resolution model, so the 25 kilometer model. In general, for the 5-member ensemble, tends to cover the observed hurricane count through most of these years. It doesn't do quite a good job in 2005, but most of the time it's pretty good. And the correlation of 0.75 is quite reasonable as well. So again, for this particular basin, as we increase the resolution, we do a better job. We're trying to pick apart the mechanisms why that happens. But then hopefully some of that is then illustrated why we think the next step is to do a coordinated experiment across multi-models where we find whether the sensitivity to resolution is really robust across models, or whether the hydrological cycle example is just our model. So just our model does that. 60 kilometers is not the resolution you're aiming at, or actually is that a more general result that many models do? So that's kind of where we're proposing this high-res MIP that Ryan Haasma at KNMI is leading. So these are the kind of things we want to look at. So we think, and I'm sure we'll hear more today and tomorrow, that sub-50 kilometer really can do a better job of some of these processes. They contribute significantly both to the large scale, the hydrological cycle, and to the small scale and impact. So it's both the large scale and the small scale. It's not just one or the other. So you can't quite do this with the regional model because that doesn't give you the feedback onto the large scale. You need that for the global drivers and for the regional variability. And we want, to do something coordinated and as simple as we can. And so I'll say a little bit more right at the end here. But so we're proposing to do a physical climate system only, AMIP as a tier 1 and then coupled for tier 2 of our simulations. And we would like to do a kind of continuous 1950 to 2050 type simulation. Now, I was having discussions last week in Japan, and I entirely appreciate that this is tough. I mean, this is high resolution, long simulations, ideally several ensemble members. It's a lot of computing needed to do this. I think there are good reasons to do it, and again, maybe we'll discuss that tomorrow. We'd also like to specify aerosol concentrations, because I know with CMIP5, with aerosol emissions, although the emissions are the same, all the models had very different aerosol concentrations, and so that makes it much more difficult to understand what is an impact of resolution and what is an impact from something else. So that's what we'd like to do. I'll say something a bit more at the end. But just to say, this work that Elizabeth Kendon has been doing at the Met Office, a couple of papers published on this. So essentially running a 1.5 kilometre model just over the southern UK, with then driven by a 12 kilometre model kind of over a much larger domain, and then that driven by, she did some initial experiments with ERA interim as the global driver, but more recently with a kind of control GCM at 60 kilometers and a future GCM, again with a time slice at 2100. And so what we're interested in here is, what does 1.5 kilometer give you that a 12 kilometer model doesn't? Or essentially, what's the explicit convection give you that a parameterized convection cannot? So just a couple of results here. So this is kind of a joint PDF, essentially of rainfall intensity versus time scale. As I'm sorry, you might not be able to read the scales here. So this is very, very strong short time scale rainfall versus long, weaker rainfall. And here are the biases from the two different models. And probably typically of a parameterized model, it can't do short time scale intense rainfall because that's not what a convective parameterization tends to do. Whereas the bias is much, much better in the 1.5 kilometer model. It really can do a much better job of this. For winter, however, the future projection is much the same. So they both project a slight increase in the intense rainfall at all time scales. So actually, although the biases are rather different, the projection for winter is quite similar. However, in summer, which over the UK, it's probably the convective part of the rainfall is more important in summer, whereas in winter it's more perhaps the large-scale rainfall. The biases are much the same in summer, but the actual projection is very different. So the low-resolution model is projecting perhaps a shift from longer timescale to shorter timescale rainfall, but really with the same intensity. Whereas the high-resolution model is really shifting from weaker to stronger convective extremes at very short timescales. So a few hours we're talking here. And that's obviously, that can cause significant flash flooding and other really serious impacts. So the projection is very different from whether you would using a 12 kilometer model or this 1.5 kilometer model. You would adapt to climate change in a very different way, looking at those two results. So that's in some sense a driver for the next level. So globally, we're not going to get to 1.5 kilometer globally for many, many years. But clearly, a 25 kilometer global model or something similar can't do everything, but it's a first step. And then maybe you still need to do kind of regional simulations at these very high resolutions, or have a NICAM model, which we don't all have. So in summary, I think this upscale project has given us lots of interesting processes to look at, and looking at the impact of resolution. And we're gradually pulling through some of this work. As I say, the Glossy 5 seasonal prediction system upgraded its resolution a couple of years ago and has really improved some of the features coming out of that. And then the regional 1.5 kilometer model, again, tells us something a bit different. So the high-res MIP kind of came out of a proposal that we put together last year. It's about 16 different European groups associated with it, this Primavera project. And then essentially the high-res MIP has kind of grown out of that as something that we'd like to do with the whole international community. And I'll kind of just leave you maybe with the this idea of the core integration, so the kind of AMIP style, the coupled phase, tier 2 style, and then some more leading edge, cutting edge work that we'd like to do. Obviously this is all very intense, and we can hopefully have some more discussions about this in the next day or two. Okay, thanks.
Any comments? Push the button.
So you show some dependency of recycling ratio according to the resolution. So and you mentioned that 60 kilometer is enough. But I want to ask you what is the resolution of the observation itself? How do you calculate the observation-based recycling ratio?
So that's a good question. So a lot of these indications down here are from reanalysis, but we know that reanalysis doesn't necessarily give you a consistent picture because the radiation is not balanced or other aspects. So for, I think, Trembirth type observations, there's some things you observe, but then some things just have to be differences to balance the budget. So actually your question is definitely well taken in that we probably don't know what the real answer is, because the model has a consistent framework, so it conserves everything, and that in some sense is our tool to try and understand resolution dependence or other things. But actually we're really struggling because we don't have a globally consistent observation or reanalysis that actually tells us what the real answer is. So yes, we don't know really what the observations are. I mean, there are, I say, some evidence. There's a couple of Trembirth things here with some measure of uncertainty, but then I think over some years that, you know, those observations have varied quite a lot as well. So yes, we don't know, I think.
Sato-san.
You mentioned both African jet and African easterly waves. So first thing, do you think both you need to resolve 16 kilometer or higher?
So I think from what we found, I mean, we find that as you can see, the jet is sensitive to resolution. I'm not sure that's true in all CMIP5 models, but that's certainly true in ours. And so we find much more precipitation over Africa at higher resolution. And I think that influences the jet, and that then clearly influences the African easterly waves. So for our model, we found that the high resolution does a better job of both of those. And I think this is probably linked to Michael Vellinger's work over the Sahel as well, that there's some interaction between the African easterly waves, the dynamics, the land surface, the precipitation. For our model, higher resolution does a better job of that interaction.
Mm-hmm. But this easterly waves itself is synoptic, so I don't think such a high resolution not so important. But you think such a coupling with convection is more important to resolve such African easterly waves?
So, I mean, at this point, all I can say is that as we increased our resolution, we get more African easterly waves with a better jet, and then more tropical cyclones further in the eastern Atlantic. What we'd like to do is to do a multi-model study to see if that's robust across models, and that, you know, that's the driver for all of this, is whether other models can manage to do African easterly waves that are 100 kilometers, or do all models need a better resolution in order to do this properly?
Okay, so we have to stop here. Sorry about that. So let's thank Malcolm again.